Welcome back to Pocket Run. Hey, where are you going? It's just math. Don't run away. Hey. Oh, well.
We're going to be doing rate problems. If you look at 18B3, a sloth traveled at a rate of 4.5 feet per minute for 2 hours. How far did it travel? Anytime you're dealing with a rate and time and a distance, you're always going to be using distance equals rate times time equation, okay? Some people like to remember this as dirt or dart. If you can just remember, distance equals rate times time. When you're dealing with the rate or velocity or speed, those are two other terms you might hear it called, velocity or speed or rate. When it's feet per minute, means feet is in the numerator and minute is in the denominator. Anytime you have the word per, feet per whatever, per means you're going to be dealing with a fractional unit, okay? 4.5 feet per minute. Alright, the distance. So on any word problem, you always want to look at what you're given and what you're being asked. So a sloth traveled at a rate of 4.5 feet. So we're given the rate, so we know that R is going to equal 4.5, I'm going to use decimals, feet per minute. We're also told that it traveled for 2 hours. So our time is 2 hours. And we're asking how far did it travel, so the D is what we're looking for. The one thing you have to look at is all your units when you're working word problems. Here, my rate is in feet per minute, my time is in hours. So my units don't match up. You need to make sure that your units match before you go and put all your numbers into the formula. So either this needs to be changed to feet per hour, or I would change hours to minutes. Usually, since the minute is in the denominator, it's going to be easier to change hours into minutes. So if we change 2 hours into minutes, 1 hour is 60 minutes, so 2 hours is 120 minutes. If you get confused on that, you can use conversion factors. 2 hours, there are 60 minutes. Wrong. There are 60 minutes in 1 hour. Now your hours cancel, and that's 2 times 60, which is 120 minutes. Okay, that's also the abbreviation, well, that's seconds. So, minutes. Alright? So, now that we have all of our units correctly, we can start putting stuff into our formula. D is what we don't know, so we can leave it as distance. And then we can put in 4.5 feet per minute for our rate times our time, which is 120 minutes. This is like over 1. So, actually, I should just look at the units. The minutes is like over 1. So you can see our minutes is going to cancel. The minutes will cancel. So we're multiplying 4.5 times 120. And that comes out to 540. And the only unit you have left is feet because the minutes canceled. It's always important to put your units on these problems. So the sloth traveled 540 feet. Alright, let's look at 18C, number 2. George walked around Dublin Lake at 7 kilometers per hour. He walked for 4 hours and 15 minutes. How far did he walk? Alright, so let's look at what we're given. 7 kilometers an hour. That's a rate. He walked 7 kilometers per hour. He walked for, his time is 4 hours and 15 minutes. Well, our rate has an hour in it, but our time is 4 hours and 15 minutes. So we need to change our minutes into hours, so our whole time is in hours, okay? We do recognize we're going to be using distance equals rate times time, but I need to make sure all my units are the same. So 15 minutes, okay? I need to put that into hours, so 15 minutes, if I want to change it into hours, I can use a conversion factor. Minutes has to go in the denominator, hours goes here, there are 60 minutes in 1 hour. So now my minutes cancel, and I can do 15 divided by 60, and that should come out 2.25. 15 minutes is 1/4 of an hour. Or we can also say 15 minutes is 0.25 hours. Okay, so we can add that 0.25 to our 4 hours. So instead of saying 4 hours and 15 minutes, we can say 4.25 hours. So now we have our time in the right units. So now we can put everything into our equation. So D is what we don't know. We know he went 7 kilometers per hour, and he went for 4.25 hours. Because hours are in the denominator here, and it's really in the numerator here, the hours will cancel, and we're left with kilometers, and that's a distance, so that's good that we're only left with kilometers. So now we're multiplying 7 times 4.25, and his distance is 29.75 kilometers. That's how far he went around the lake. Okay, now we're looking at 18B, number 5. So those last two problems, we were dealing with only one person. Now we're dealing with two people. So we have Joanne and Jenny both walked to the park. Alright? Joanne walked 4 miles an hour and Jenny walked 3 miles an hour. Okay, so I'm just going to stop right there and I'm going to draw a picture. We have two people who walked to the park. So they both went the same distance. They both had the same starting spot. They both started here, and then they went like here, and then they both went to the park. So here was the park. So if we can all agree, Joanne and Jenny started at the same place, and they ended at the same place. They ended at the park, so therefore we know that they went the same distance. So I'm going to use this diagram to draw this diagram. So this line represents the distance that Joanne went, and we need to use subscripts. You can either use 1 and 2, but that doesn't tell me which one is which. So I'm going to use a JO that represents Joanne's distance, and then I'm going to use JE to represent Jenny's distance. These are just subscripts. They're just labels. We don't use them to make calculations. This just says this is the distance Joanne went, this is the distance that Jenny went. And we know that their distances are equal to each other. So I'm going to go ahead and say that Joanne's distance is equal to Jenny's distance. Because they went the same distance. They both started at the same place and they both ended at the same place. Okay? But what do we know about Joanne's distance? We know that it equals the rate times time that Joanne went. So I'm going to show it like this. Joanne's distance equals the rate she went times the time she went. The same is true for Jenny. Jenny's distance equals the rate she walked times the time she walked. Now let's go back to the problem and see what other information that we know. Okay? We know it says Joanne walked 4 miles an hour. Okay, so up here in Joanne's information, I'm going to write down that she went, the rate of Joanne equals 4 miles an hour. Then it said that Jenny walked 3 miles an hour. So down here, I'm going to keep all of Joanne's information up here, and then I'm going to keep all of Jenny's information down here. Okay? So Jenny's, her rate was 3 miles an hour. Okay? Then it said it took Joanne 2 hours to make the trip. Okay, Joanne, we just were told her time. So we were told the time of Joanne was 2 hours. Then it says, how long did it take Jenny? We don't know Jenny's time, so I'm just going to come down here and put a question mark, because that's what I don't know. And then it also says, how far away is the trip? Or how far away is the park? Okay, well, I can actually figure out how far away the park is right now, because the distance of Joanne equals the rate times time of Joanne. Well, we're given the rate of Joanne and we're given the time of Joanne, so I can actually figure out the distance because they both went the same distance. It doesn't matter if I'm using Joanne's distance or Jenny's distance because they're both equal to each other. So I can use the information from Joanne to actually figure out the distance. Okay, so I can go ahead and figure out the distance using Joanne's information. The distance of Joanne equals the rate times time of Joanne. And Joanne's rate is 4 miles an hour times her time, 2 hours. Remember, when you have miles per hour, that hour is in the denominator. So that hour and that hour cancels to where we're only left with miles. So 4 times 2 is 8. So the distance of Joanne, which is the same as the distance of Jenny, the distance to the park is 8 miles. We got that from 4 times 2, and then we only have miles left as our unit, okay? But then the other question asks, it asks 2 questions. The other question is, how long did it take Jenny? Okay? Well, we're going to go back to this main equation. We said the distances are equal to each other. But what does the distance of Joanne equal? Okay? If I rewrite that, the distance of Joanne equals the distance of Jenny. Well, doesn't distance equal rate times time? So this is Joanne's rate times the time of Joanne. This also equals rate times time, but of Jenny. So that would be Jenny's rate times Jenny's time. So basically all we did is we took our rate times time. We said right here that the distance of Joanne equals her rate times time. And instead of putting the distance, we put rate times time. Same here. Jenny's distance equals her rate times time. So we replace distance with rate times time. So now we can just plug in all the information that we know. Do we know Joanne's rate? Yes. It was 4 miles an hour. Do we know Joanne's time? Yes. It was 2 hours. Do we know Jenny's rate? Yes. She went 3 miles an hour. And do we know Jenny's time? No. That's what we're trying to solve. So I have an equation here with only one unknown, and we should only have one unknown. So now it's just a matter of that hours and that hours will cancel. So now we can multiply these numbers together, and that will be 8. As long as all of my units are the same, what unit should I come up with time? Since I'm dealing with hours, then my time unit will be hours. So for a moment, I'm just going to drop all my units. Okay, 4 times 2 is 8, equals 3 Jenny's time. So to solve for Jenny's time, we're dividing by 3. Divide each side by 3. So basically over here, let me come over here. So we have 8 over 3 equals Jenny's time. And it's okay that you're going to get a decimal, because if you do 8 divided by 3, you get, I'm going to round it to 2.7 hours is Jenny's time. Or you can actually turn your 0.7 hours into minutes. If you want to turn 0.7 hours into minutes, what is 7/10 of an hour? Well, you multiply that by 60 to convert it to minutes. So multiplying that by 60 means 42 minutes. So you could say that Jenny went 2 hours and 42 minutes. That was her time. Okay, we're looking at 18E, and they're calling this number 4 and 5. So if you look at the first sentence, Frank and Glenda took different flights to New England. Yes, they took different flights, but the key is they both left from the same place, and then they both went to New England. In this lesson, when 2 people are going somewhere, they are going to go the same distance. They both are leaving from the same starting point, and they both are going to get to the same ending point. So they both left for New England. Even though they have different flights, they still went the same distance. It's just they didn't go the same time or the same speed. So, but they have the same distance. Okay, so we can see that they went the same distance. So up here, we're going to say this is Frank's distance. And down here, we're going to call this Glenda's distance. So Frank's distance will equal his rate times his time. and Glenda's distance will equal her rate times her time. One statement we can make is that Frank's distance is equal to Glenda's distance. Well, we can substitute in rate times time for Frank. So rates Frank times his time is equal to his distance. Over here for Glenda, we can substitute in her rate times her time. Okay? So now let's find out what other information we know from the problem. So Frank left at 8:30 a.m. So over here, Frank, I'm going to write all his information up here. He left at 8:30 a.m. and then Glenda left at 7 a.m. She left at 7. And then in the problem it says they both arrived to the airport at noon. So they both arrived here in New England at noon. So if Frank left at 8:30 and he arrived at noon, how much time did that take him? So Frank's time, that's 3.5 hours. Okay, so Frank's time is 3.5 hours. So I'm going to write that up there with his information. If Glenda left at 7 and she got there at noon, how long is that? It's 5 hours. Okay, so Glenda's time is 5 hours. Then it says Frank's jet averaged 500 miles an hour. Okay, so Frank's rate is 500 miles an hour. Okay, how far is the trip and how fast did Glenda travel? So we don't know Glenda's rate. We don't know her rate. Alright, I gotta switch colors here to green because that blue is not showing up very well. Alright, so we don't know Glenda's rate. And then it also wanted to know how far is the trip. Well, up here, distance equals rate times time. We actually have enough information up here to determine the distance because we have all of Frank's information. Frank's rate times his time will equal the distance. And the distance is the same for both Frank and Glenda. So we can actually use Frank's information because Frank's distance equals Glenda's distance. And so Frank's distance is Frank's rate times his time. Okay, so we can take Frank's rate of 500 miles an hour times Frank's time of 3.5 hours. This hour, which is in the denominator, and this hour cancels to leave only miles. So the distance, which they're the same, Frank's distance equals Glenda's distance, so I'm just going to call it distance, is 500 times 3.5. That came out to 1,750 miles. So we know that that's the distance. Okay, to figure out Glenda's rate, a little bit more involved. We can go back over here to this information. We know that their distances are equal to each other. Therefore, we know that their rate times time is equal to each other. All I did was, instead of putting Frank's distance, I put rate times time. So now let's go back to our information that we have and fill it in. We know here's what I like to do. We know Frank's rate, we know Frank's rate, we know Frank's time, we don't know Glenda's rate, that's our question mark, and we know Glenda's time. So there's only one unknown that I don't know in this whole equation, so I can fill in all what I know. So Frank's rate is 500 miles an hour times Frank's time, 3.5 hours. I don't know Glenda's rate, and then her time was, that's over here, 5 hours. Okay? So I'm going to drop all my units for just a second. Everything is in the right units. I have miles and hours, and the time is all in hours. So the fact that I'm dealing with miles and hours and I'm solving for a rate, when I'm done, I should end up with a miles per hour with all my units. Okay? So here I'm just multiplying my numbers together. 500 times 3.5. That was 1750 equals 5 Glenda's rate. Well, I'm solving for Glenda's rate, which that means I'm dividing by 5. That goes away. So 1750 divided by 5 came out to 350, that's a rate. The unit for a rate needs to be miles per hour. So now I know Glenda's rate on her plane was 350 miles an hour. They went the same distance, they just didn't do it in the same amount of time or the same speed. So therefore we've just solved both of the questions it was asking. Alright, now let's look at 18E. They're calling this number 6 and 7. So again, we have the same two people. So we're dealing with Frank and Glenda again. But now on the way back home, Frank took a bus and Glenda took a train. But they still left, they went the same distance. They both left New England and then they went back home. Okay, so here was New England and then they went back home. So they just did it at different speeds and different times, but they did the same distance. So we're going to be dealing with the same thing. Their distances are equal. So here's going to be Frank's information. Here's going to be Glenda's information. His distance is, so let's just go over here. We know that Frank's distance is going to be equal to Glenda's distance. Well, Frank's distance is his rate times his time, and Glenda's distance is her rate times her time. And these are all just subscripts to label. This is Frank, this is Glenda. Okay, so let's go back to the problem and find out all of our information. Okay, so Frank took a bus. So here we are on the bus. So this is Frank's information. The bus averaged 50 miles an hour. So Frank's rate is 50 miles an hour because that was how fast the bus went. Okay, then it says the train arrived home 10 hours before the bus, I'm going to get back to this information, and traveled 20 miles an hour faster. I tried to underline key words. The train went 20 miles an hour faster than the bus. So Glenda went 20 miles an hour faster. She didn't go just 20 miles an hour. She went 20 miles an hour faster. So 20 miles an hour faster than this would be now 70 miles an hour. So Glenda went a rate of 70 miles an hour. Okay, now you get to what was the rate of the train and how long did it take Frank to get home. Okay, so we already answered what was the rate of the train because we just said that. Glenda went 70 miles an hour. So that was one of your questions. Okay, what was the rate of the train? The train went 20 miles an hour faster than the bus. So the rate of the train was 70 miles an hour. Okay, then the other question is, how long did it take Frank to get home? Okay, so right now we don't know Frank's time and we don't know Glenda's time. I probably should have used bus and train for all my subscripts, but okay. So I'm using Frank and Glenda instead of bus and train. So here I'm going to write this. So the bus, which is Frank, and then the train, which is Glenda. Okay, that'll help us. So this sentence right here, the train arrived home 10 hours before the bus. This is going to be our key of figuring out the time. Because right now, if you look at this equation, we know Frank's rate, we know Glenda's rate, but we don't know their time. And we cannot have two unknowns because we only have one equation. Okay, so in this equation right here, we have two unknowns. If we have two unknowns, you have to have two equations to solve it. We get our second equation from the time, the information on the time of the train. So here, the train arrived home 10 hours before the bus. So if the train arrived home 10 hours before the bus, it means the train took less time, the bus took more time, okay? So Glenda's traveling time was less than Frank's. That makes sense because usually a train will travel faster than a bus. So we can say that Glenda's time is Frank's time minus the 10 hours. Okay, this shows that Glenda did take less time. If she took Frank's time, minus 10 hours because she got there before him. Okay, so once you write this equation, make sure it makes sense. So whose time, from the information that we were given, whose time should be larger, should be, or smaller, if you want to think of it. Glenda's time is less. So the train took less time because it got there 10 hours before. Does this equation say that? Glenda's time would be less than Frank's, because if you took Frank's time and subtracted 10 hours, the number will be smaller. So yes, Glenda's time is shorter. Okay? Now that we have that equation, we have two equations and two unknowns, and so we can use substitution to solve this, because we can take this. If we're told that Glenda's time equals this, we can take this and put it in right there for T for Glenda's time. Okay? So now we have, I'm going to start putting numbers into all this. We know Frank's rate, which is 50. I'm just going to drop my units for ease of solving the equation. 50 and then Frank's time equals, we know Glenda's rate, which is 70. And then instead of writing the Glenda's time, we're substituting this whole thing. Frank's time minus 10. Now we have one equation and one unknown. How do we solve this? We have to distribute that 70. So we have 50 T sub F equals 70 TF minus 700. Get our variables on the same side. So subtract our 70 TF to the other side. That goes away. 50 minus 70 is a negative 20. And then over here we have a negative 700. Divide both sides by our negative 20. So now Frank's time, we should end up with a positive. If you ever end up with a negative time, you did something wrong. A negative divided by a negative is a positive. And 700 divided by 20 is 35. And so we're dealing with time. Everything was in miles per hour. All of our units are the same. So time has what kind of units? It'll be hours. So Frank's time was 35 hours. That's what the question asked for. How long did it take Frank to get home? If it did ask for Glenda, we can go back to that equation right there. We can take Frank's time, subtract 10, and now we would get Glenda's time. So, because Glenda, it took her 10 hours less to get there. She got there 10 hours before, so it would have taken her 25 hours. The problem didn't ask for that, but the problem did ask for what was the rate of the train, which was this rate right here, and then what was Frank's time. Okay, we're looking at 18A6, and we're looking at a problem with Jerry and Joe. Okay, so Jerry left at a certain time, traveling at a certain speed. Then Joe left 1 hour later, and he passed Jerry at a certain time. How fast was Joe traveling? So here's what's happening. So Jerry left and traveled a certain distance, and then Joe left the same starting point and then got to the point where he passed Jerry. So they had the same starting point. They didn't start at the same time, nor did they have the same speed, but they started at the same starting point, and then we're going to calculate their same ending point, because this ending point is where Joe caught up to Jerry and passed Jerry. So their distances are going to be the same. Again, in lesson 18, when we're dealing with two people or two objects, they will be going the same distance. So we will be dealing with Jerry's distance, and then we're going to deal with Joe's distance. And they are equal to each other. So we can make the statement that Jerry's distance equals Joe's distance. Okay? Well, Jerry's distance has a rate times a time, and Joe's distance has a rate times a time. So over here we can replace Jerry's distance with his rate times time, and we can replace Joe's distance with the rate times time. Now let's look at the rest of the information in the problem. Okay, Jerry left at 4 p.m. Okay, so up here, Jerry left at 4. Okay, and his rate was, Jerry's rate was 55 miles an hour. Joe left 1 hour later. Well, if Jerry left at 4, what time did Joe leave? 1 hour later would be 5 o'clock. Okay, then it says they passed Jerry at 9 p.m. So here we go. Where they caught up to each other was 9 p.m. So now we can figure out their times. So if Jerry left at 4 and then they both were at the same exact place at 9, it means it took Jerry from 4 to 9. That's his time. So his time is 5 hours. So Jerry's time is 5 hours. Okay, Joe's time, he left at 5 and got there at 9. So obviously he was running faster. So from 5 p.m. to 9 p.m., that is 4 hours. So Joe's time is 4 hours. Okay, were we told anything about Joe's rate? No, that's what the question asked. We don't know Joe's rate. That's what they're asking for. So go back to our equations and you can see we know Jerry's rate. We know Jerry's time. We don't know Joe's rate, but we do know Joe's time. So we know everything except for one thing. And that's good, that we should only have one unknown. If we have one unknown, we can use this to solve. If we have more than one unknown, we have to come up with another equation. So let's fill in what we know. I'm just going to drop all my units for ease of calculating. Everything was in the same units. My rates were in miles per hour. My times were in hours. So everything matches. So Jerry's rate is 55. Jerry's time, over here my information was 5. Joe's rate, over here, that's what we don't know. So I'm just going to leave that as my unknown. And then Joe's time was 4 hours. So this just becomes 55 times 5, 100 and, not 110, 100, oh, not even 100, 275 equals 4RJ. I'm going to write it like that because then you can tell what do you have to do with that 4 to get rid of it. You have to divide it away. R times 4 is the same thing as 4 times R by the commutative property. Means we have to divide it by this side. So then we take our 275 and divide it by 4. Came out to 68.75. We're dealing with the rate. What are our units for a rate? Miles per hour. I don't guess they were jogging. Maybe I thought they were jogging. They're not jogging at this speed. So you're in a car, whatever. Yeah, that makes more sense. Cars at 55 miles an hour, 68 miles an hour. So there you go. There's Joe's rate. Okay, now let's look at 18A5. Again, we're dealing with two objects, two trains. So in this lesson, most of the, or they're all, when you're dealing with two objects, they're going to be going the same distance. Because two trains were scheduled between Lancaster and Philadelphia. So there you go. We've got two trains and they left Lancaster. They left Lancaster and then they went to Philadelphia. So that tells you right there they are going the same distance. They probably didn't travel the same amount of time, nor did they probably go the same speed. So we're just going to call this one D1 for train 1, since they call it two trains, and then we'll call this one D2 for train 2. So we can go ahead and make the statement that D1 equals D2. Well, the first train, his distance equals a rate times a time, and I'm going to put these labels on there, rate 1 times time 1. And then the second train is going to have a distance of rate times time. Okay, I usually like to write all that down, and then I'll go back to the problem and get all my information. Okay, so the next information it says is one train, let's just call this train 1, okay? One train averaged 45 miles an hour. So there you go. For train 1, its rate was 45 miles an hour. And then the other train averaged 35 miles an hour. So let's just say train 2, so 2, its rate was 35 miles an hour, okay? Now, so over here in our equation, we know the rate for the first train and we know the rate for the second train. Now let's look at our time information. It says the second train took 4/10 of an hour longer. How far is it between stations? So we're wanting to know the distance, but we can't know the distance until we can know the time. So if the second train, so if we want to write an equation, because right now we have 2 unknowns. If we have 2 unknowns, we have to have a second equation. So we need to write our second equation from the time information. So the second train, so we're going to say T2 took 4/10 of an hour longer than the first train. So the second train's time should be longer. It took longer. So the second train, his time is the first train plus 0.4. 4/10 of an hour longer. So when all this is said and done, you need to think about which train took longer. Well, here it says the second train took longer. So does this equation match what the words say? Will T2 be bigger than T1? Yes, because if you took T1 and then added time to it, it will be longer, okay? So now we can take this information and use substitution to solve. Because we said T2 equals T1 plus 0.4, so we can take this, T2 is this, take this and put it in for T2. So now going back to this equation right here and filling in what we know. So I know that my first rate 1 train was 45. I don't know T1, so I'm going to leave it as T1. Again, I'm dropping my units for ease of calculations. Everything was in miles per hour, so I'm good. My rate of train 2 was 35. And instead of writing T2, I'm going to write this whole thing because T2 is this. Use your parentheses. Now I can use distribution. Distribute that 35. So 45 T1 equals 35 T1 plus 35 times 0.4 came out to 14. Now I want to get my T1s on the same side. I need to get all my T1s together, all my variables together. It's like getting all my x's to one side. So those go away there. 45 minus 35 would be 10. T1 equals 14. Divide both sides by 10. Come over here, so T1 equals 14 divided by 10. That comes out to 1.4 hours. Well, that's not what the problem's asking. Okay, the problem says, how far is it between stations? Okay, now that we know that T1 equals 1.4 hours, remember the distance is the same. So we just need a rate and time for one of our informations to be able to find the distance, because distance equals rate times time. So now that we know a time for one of them, we can use this information to say distance equals rate times time to do our 45 times our 1.4. And this was miles per hour and that was hours. So our hours will cancel to leave miles. So we can take our 45 times our 1.4 and that will be 63, and the unit that was left is miles for distance. So even if we had went and solved T2 and figured out T2 and then used it here with the information from the train 2, we would still come up with the same answer, 63 miles, because the distance should be the same. So how far is it between stations? 63 miles.